Okay, it gives me great pleasure to introduce the next speaker. It's Receptor-Ligand Venkataraman from the University of St Andrews, and he's going to be talking about the free boundary problems on a model of receptor-ligand dynamics.
Thank you very much, John. And I'd like to thank the organizers of this workshop and the program organizers for inviting me to talk here. I've been here for most of the 4 or 5 months, and it's really been a really stimulating place to stay. I've learned a lot. It's been fantastic scientifically and socially. As John said, I'm going to talk to you about free boundary problems that arise from a model for receptor-ligand dynamics. And this is joint work with Charlie Elliott and Thomas Rana, who are both at this program earlier on. It's really nice to be talking about this work at the INI because last year, I think from January to July, there was a program on free boundary problems where Charlie, myself, and Tom were all participants. And so we started this work during that program, hence the free boundary problems. But we were lucky enough to be working on a problem that was related to cell biology, so I'm also able to talk about that work at this workshop as well. So I was going to have a motivation slide in here about why it's interesting to study receptor-ligand dynamics to understand biological problems. But we've heard 3 fantastic talks where people have demonstrated that coupling bulk and surface processes to model receptor-ligand dynamics is really important to understand problems in biology. So I think yesterday Dumitru talked about how receptor-ligand dynamics are crucial in cancer biology. Dagmar showed how in branching morphogenesis we need to understand receptor-ligand interactions. And Alan just talked about how they're important in cell polarization. I'm not going to have a specific application in mind. I'm instead going to work with a very simple model for receptor-ligand dynamics, and I stress simple, because the goal here is going to be to do some mathematics rather than model a specific application. The model I have in mind is as follows. I have a cell whose boundary I'll denote by gamma, and this is some smooth stationary surface. I'm not thinking of moving cells for the purposes of this talk. And it lives in an ECM, which I'm going to denote by omega. I'm going to think of omega as a bounded domain, and the outer boundary of omega is going to be d0 omega. For instance, we could think of this outer boundary as being Lipschitz. My model is very simple. I'm going to consider a 3-species model where I have a bulk ligand field, Cl, which is defined in omega, a surface receptor field, Cr, which is defined on gamma, and a receptor complex field, CRL, which is also defined on gamma. Simple equations. The bulk ligand just diffuses in omega. On the outer boundary, I have some very simple boundary conditions. So I either have constant Dirichlet boundary conditions, where I would be saying that the source of ligands far away from the cell, the concentration of ligands far away from the cell is uniform, or I have zero flux boundary conditions. But what I would be saying is that we're in some isolated region of space. The interesting stuff happens on this inner boundary gamma. Here I have a nonlinear boundary condition for the flux of ligands, and what I'm basically saying is that I lose ligands if they react with receptors to form receptor-ligand complexes, and I gain ligands when these receptor-ligand complexes dissociate, giving me back ligands in the bulk and receptors on the surface. I have equations for the receptor-ligand complex density. I'm going to assume they're mobile, so they move along the surface of the cell by lateral diffusion. And the source term, well, for the same considerations that we got this flux term, the source term just looks like this. I lose surface receptors when they react with ligands to form receptor-ligand complexes, and I gain them when these complexes dissociate. I have a very similar equation for the receptor-ligand complex density, but of course the sign is just opposite. This is already a simple model, but I'm going to make it even simpler. And what I'm going to assume is that I'm in a regime where the binding affinity is very large. So what I'm basically saying here is that when receptors and ligands bind to form these complexes, they don't want to unbind. So this on rate, K1, dominates the off rate, K2. I'm going to assume that this rate, K2, is so small that we can just neglect it. We set it to 0. If we do this, the red equation decouples from all the others, and so we can just neglect the receptor-ligand complexes. Once we've solved the rest of the system, we could just solve a linear parabolic equation for the complex density. Okay, so I want to do some mathematics. All right, I should say first, this is a very simple model. I've reduced everything to just a 2-component system. It's much simpler than the models we've seen yesterday and earlier today. But I think some of the key features of receptor-ligand dynamics are still there. So we have coupling of a diffusive process in this domain omega to a diffusive process on the surface gamma, and this coupling is nonlinear through these boundary conditions here. I want to do some mathematics, so I'm going to non-dimensionalize, so introduce characteristic length scales, time scales, and concentrations. And then you can write the system I just showed you as this non-dimensional system here. U is my non-dimensional bulk ligand concentration, W is my non-dimensional surface receptor density, and I see I have these 4 non-negative non-dimensional parameters. Delta omega is a coefficient which sits in front of the time derivative of the bulk equation. Delta K you can think of as 1 over the reaction rate between the bulk ligands and the surface receptors. Delta gamma is the non-dimensional surface diffusivity of surface receptors, and mu somehow gives you the strength between the coupling of the bulk and the surface. And so one can plug in experimental values for all these characteristic scales, and if you do that, what you see is that there are 3 biologically relevant limits of this equation that one would want to look at. The first is what I'll call the fast reaction limit, where this parameter delta K is very small. So what we're basically saying there is we're thinking of the reaction rate between bulk ligands and surface receptors going to infinity. The second, which would be valid on short time horizons, so sub-minutes, is to think of delta K being very small, the diffusion on the surface being very small, but delta omega and mu being bounded well away from 0. And if you look at longer time horizons, so half an hour or hours, then you can think of all of the deltas being very small, but mu still being approximately 1. And later on in this talk, we're going to rigorously see what happens when we pass to these 3 different asymptotic limits. So that brings me to the outline of the talk. We're going to start by taking this very simple model I showed you for receptor-ligand dynamics, where all of the parameters are held strictly positive, and try and prove that it's well posed. So there exists a solution, and the solution is unique. Then we'll look at these asymptotic limits and try and give a mathematically rigorous derivation that as we pass through these limits, we converge to these 3 limiting problems. These problems turn out to be interesting because they take the form of coupled bulk surface free boundary problems. And I'll say more about this as we go through the talk. I'll then digress very briefly and talk to you about some classical free boundary problems, namely the Stefan problem and the Healy-Shaw problem, because we'll be able to relate our limiting problems to these classical free boundary problems. Finally, I'll show you some pretty pictures of simulations of all of these different problems and conclude. So all of this seems a little bit mathematical and a little bit far away from maybe the point of this workshop, which is to somehow relate things to biological problems. I would say my defense against that is in these pictures here. So I think what we're doing is applicable to biology, and it's useful even in more applied works because these types of model reductions can give you massive advantages if you're doing computation. So in the top row, I'm showing you a simulation of the model I've just shown you, where I basically have my cell, who's this blue guy, and he lives in a spherical domain. So my domain omega is a sphere with this cell-shaped hole cut out of it. I've not shown you the top half of the sphere because then you wouldn't be able to see the cell. Everything would be uninteresting. So I've made the top half of the sphere transparent. And we're simulating that coupled parabolic system of equations. We start from some initial data, and we solve forward in time to whatever time we're interested in. What you see is that you lose ligands near where receptors are present on the surface because they react with the receptors to form these receptor-ligand complexes. Eventually, all the receptors on the surface become complexes, so they all disappear, and you just have no receptors left on the surface. But maybe I'm only interested in these 4 snapshots in time. I don't actually need to solve the problem for all times. However, because I have a parabolic equation, I can't get away from that. I have to start from my initial data and solve the problem forwards in time. So this takes hours to do, typically. On the other hand, we'll show that when we do these model reductions, we get to limiting problems where the solution can be obtained at any given time, independent of the value at all the other times. So if I want to obtain these 4 pictures here, I don't have to solve a coupled system of parabolic equations. I just have to solve 4 problems at 4 independent times, and these problems can all be solved independently of each other. So rather than everything taking hours to compute, you can generate these sorts of simulation pictures in seconds. And that's one advantage, I think, in terms of these types of model reductions that I'll present in this talk. But let's start with the mathematics now. Let's look at that simple model for bulk surface receptor ligand dynamics, and let's try and prove it's well posed. So the system of equations I showed you looked like this. Because I'm never going to drop mu, I always keep mu in all of my asymptotic limits. For simplicity, I'm just going to set it to be 1. You can work with any strictly positive value of mu, and this will all still work. I have to make one further restriction, and that's as follows. I can't show that solutions to this equation remain positive, given positive initial data. unless I assume something about the regularity of the solutions to these equations. So I'm going to stick that in the definition of the problem to get a physically meaningful problem. I'm going to say that I want to find functions u and w who are positive that satisfy this equation here. And for the initial data, these guys represent concentrations, so I'm just going to think of them as bounded non-negative functions.
For memory, mu equal to 1 is the diffusion constant?
No, mu is was the surface bulk coupling. So it's not quite, it's related to the diffusion constant, but it's not quite. It also takes the characteristic concentrations into account. So my notion of a solution to this problem here is going to be defined in this way. So I'm going to look at weak solutions. I take test functions, multiply by test functions, integrate over the domain, and integrate by parts. And I'll call any pair UW that satisfy these two weak formulations here a weak solution of this problem here. Okay, and these are just the usual spaces for weak solutions to parabolic equations, and I need u and w to be positive in the sense of L2. Then we have a theorem, and the theorem says that there exists a unique weak solution pair to this problem in the sense I just defined, and furthermore they satisfy these bounds here. So essentially u and w are bounded, and they're bounded by their initial data. And this theorem turns out to be really easy to prove, so I'll just give you a brief idea of the proof. You take your problem with the nonlinear coupling, and you replace the nonlinear term with this guy here, where m is some cutoff function, such that m of eta is 0 for eta negative, m of eta is eta for eta in some bounded interval, and for eta bigger than m naught, m of eta is just this m naught. Okay, for this problem here, we haven't assumed positivity anymore, and it's easy to show that there exists a solution. You can use standard methods. So a Galerkin argument, for example, works. And if you use a parabolic comparison argument, so you test with the right test functions, you also get these pointwise bounds. So solutions remain positive, and they're bounded by their initial data. But then one realizes that actually this m naught was free, and I could choose m naught to be bigger than the L infinity norm of the initial data for w, and if you do that, you see that m of w is equal to w, and so you've actually constructed a solution to the original problem with the nonlinear coupling. I won't go through the details of how we show that the solution to the original problem is unique. That's essentially an L1 argument, and it follows ideas used by Evans in a paper in 1980 for coupled systems of parabolic equations posed in the same domain. I'm happy to talk about it with anyone who's interested. So now that we have existence and uniqueness of a solution to that simple model, we want to look at the asymptotic limits. We want to look at these three biologically meaningful limiting parameter regimes we discussed earlier. The reason these problems are interesting from a mathematical perspective is because these limiting problems, when we send this reaction rate to infinity, or delta k to 0, they lead to coupled bulk surface free boundary problems. And the reason that happens is because in the resulting limit, we have that u, the bulk ligand concentration, stays positive, w, the surface receptor density, stays positive, but uw, the product, has to vanish almost everywhere. And to see why that's the case, if we go back to this problem, we want this term to make sense in the limit when we send delta k to 0, and if we want to get a sensible term out of this, u and w, their supports have to become disjoint. So you get a free boundary problem because essentially on gamma, you have a region where u is positive and w is 0, and a region where w is positive and satisfies an equation, and u is 0. And the free boundary is the boundary between the support of u and the support of w. Many people have looked at these types of problems in the literature, but as far as I'm aware, people have only looked at coupled systems of parabolic equations or coupled systems of elliptic equations posed in the same domain. The technical novelty of this work is that we have this coupling on the boundary of the bulk domain. So we have the coupling between a bulk PD and a surface PD, and that adds technical difficulties to the analysis. So some of the people who have looked at these types of problems are listed here. This is a very incomplete set of references. I should mention there's been a lot of work by the group of Hilhorst and co-workers where they take coupled systems of parabolic equations with essentially the same nonlinearities we're looking at, and if you pass to the fast reaction limit, you get free boundary problems, which are essentially the Stefan problem. And we'll see that that's related to what comes out when we pass to our fast reaction limit. So the basic strategy of passing to these limits is to take your original equations and try and prove some a priori estimates that are uniform in these parameters we're going to send to 0. And this will give you the necessary compactness to pass to the limit. So the first estimate we can get is that in all the cases we can get an L2 H1 norm bound on the bulk ligand concentration u. And this constant c obviously is independent of all of these parameters. This is really easy. You take the equation for u and you essentially test with u. That gives you a bound like this straight away. In one of the cases, we're going to send delta omega to 0. And so that looks like a problem because all I have is an L2 bound on the gradient of u. But in that case, we'll see that we don't get a well-posed problem if we have Neumann boundary conditions on the outer boundary. So in that case, we're only going to consider Dirichlet boundary conditions on the outer boundary. And then I have a Poincaré type inequality for u. So an L2 bound on the gradient of u is enough to conclude this type of an L2 H1 bound on the function. For w, we can get an estimate like this. So again, you just take the equation for w, test with w, and use the fact that solutions are positive. As long as I'm keeping surface diffusion, this gives me an L2 H1 bound on w. When I drop delta gamma, I no longer get it. Yeah?
So you used a Dirichlet boundary condition, right? In the previous slide. Yeah.
Yes. So there are, if I go back, we consider either Dirichlet or Neumann.
Yeah, but I mean for your stability argument later on.
Yeah.
And could you use a Robin, a mixed boundary condition?
Yeah, as long as you have control on. So if you had a Robin type boundary condition with you there, you'd have a Poincaré inequality, and this would all work. But it's the pure Neumann case which is where this wouldn't work. Yeah.
Yeah, that's right.
But just to add to that, is it because of technical difficulties or there's a qualitative difference?
No, I mean the problem is. Okay, so the problem would be trivial, I think, if you took the Neumann case. We'll see the limiting problem when we send delta omega to 0. And you lose the time derivative, and all you have on boundary conditions, the boundary conditions are the normal derivative of u. So you shift the solution by any constant, and it's still a solution.
Sure, you did, right?
Okay.
Sorry.
So no problem. So when we drop delta gamma, we don't get an H1 bound on W. All we get is some LP bound on W. To pass the limit, we also need some estimate on the nonlinear term, and we can get basically that the L1 norm of the product of U and W is bounded by delta K times the L1 norm of the initial data. So when we send delta K to 0, we're going to get that the L1 norm of U and W goes to 0, which gives us that the product of U and W converges almost everywhere. To get a bound like this, you take the equation for W, you integrate in space and time. Because gamma is a closed surface, you lose the Laplace-Beltrami at W, and then you use positivity, and directly you get a bound like this straight out of such a calculation. In practice, all of these bounds will give me weak convergence of U and W and some convergence of the product of U and W, but that's not going to be enough because my original problem is nonlinear, so I need some form of strong convergence. And the way one would typically prove strong convergence for this type of problem is to get a bound on the time derivative of U or the time derivative of W. But you can't get such a bound for this equation unless you make quite restrictive assumptions on the initial data. What we can do instead is get these bounds on time translates of U and W. So what does it say? It says that delta omega times the L2 norm of the time translates of U squared plus the L2 norm of the time translates of W squared can be bounded by some constant times the step size of the translate. So as long as, but this bound of course for U is only valid if I'm keeping delta omega. And we'll see that this is enough to get the necessary strong convergence to pass to the limit. Okay. So the first limiting problem I wanted to tell you about was the fast reaction case when we just sent delta K to 0. In that case, the limiting problem you get out is this guy here. Let me just maybe draw this graph B to U, because it'll come up quite a lot. So this problem that we get out in the limit is a parabolic equation with dynamic boundary conditions involving the Laplace-Beltrami. And we have this constraint that V, which is the guy who lives on the boundary, is in B to U, where B to U is this graph here. So V is basically minus the limit of W. So it's minus the surface receptor concentration. The reason I've changed notation again is just that everything looks nicer if we write the PDEs with V instead of W. And all this constraint is saying is our complementarity condition. So V is minus W. We need V to be negative. We need U to be positive. And we need the product of U and V to vanish almost everywhere. So all this is saying is complementarity. It's just encoded in this graph here. Okay. So we can make this rigorous, that as we send this parameter delta k to 0, the solutions we've just constructed to this problem converge to solutions of this problem here. To do this, we need to define a weak solution to this problem here, and I can't do that without introducing quite a lot of notation. So I define a Sobolev space of H1 functions who have traces in H1, and then I'll call a pair of functions u bar, v bar in these spaces, don't worry too much about the spaces, a weak solution to this problem here if they satisfy this weak formulation for all suitable test functions. And one thing to note that's kind of interesting is we never get a bound on the time derivative of u or the time derivative of v. So I have to write this weak formulation weak in time. I have to integrate by parts and pull the time derivatives onto the test functions. They satisfy this weak formulation here, and I have this constraint that v bar is in beta u bar. So we can prove a theorem that as we send the reaction rate to infinity, or delta k to 0, this solution pair uw that we just constructed to this equation converge up to a subsequence to a pair u bar, such that u bar w bar, such that u converges weakly to u bar in L2 H1. We have weak convergence of w in L2 H1 gamma, strong convergence of u in L2 omega across 0t, and strong convergence of w in L2 gamma across 0t. Moreover, the limiting pair u bar v bar, with v bar defined to be minus w bar, are a solution to this problem here. And a very brief idea of how we prove such a theorem. The weak convergence results I stated followed directly from the a priori estimates. We had boundedness in L2 H1 for u and w, so standard compactness results tell us that we can extract a weakly convergent subsequence. This allows us to pass to the limit in the weak formulation and verify that the limiting pair satisfy this weak formulation here. But now I need to verify that this constraint holds in the limit. And for that I need these strong convergence results. In this case, because we had this weak convergence in L2 H1 and we had this estimate on the time translates, that implies that both u and w strongly converge in L2. And that's basically a result from this Aubin-Lyon-Simon compactness theory. It uses the fact that H1 is compactly embedded into L2. Now, because we have this strong convergence, we then recall our estimate on the nonlinear term. This implies that u and w converge to 0 almost everywhere. And because w converges strongly in L2 gamma cross 0t, I have the product of weakly and strongly converging subsequences. So the product of the limits is the limit of the products. And that in effect gives me that v bar is in beta u bar. This is a very brief run through the calculation. There are more technical details in the paper. In the case where we're sending both delta k and delta gamma to 0, so this is fast reaction, slow surface diffusion, one gets out a limiting problem which looks like this. Okay? So it's very similar, but now we've also sent delta gamma to 0. So on the boundary, we no longer have the Laplace-Beltrami of v appearing. We have the same constraint that basically encodes this complementarity between u and v. And we can define a weak solution to this problem in this way. So we'll call a pair u tilde, v tilde in these spaces here. A weak solution to this problem if for all sufficiently smooth test functions they satisfy this weak formulation here. Again, I don't get an estimate on the time derivative, so I have to interpret this as weak in time. I have to integrate by parts and pull the time derivative onto the test function. And we have to have this constraint that v tilde is in beta u tilde. So we can make this convergence rigorous. As we send both of these parameters to 0, this solution pair converges to a pair u tilde w tilde. I still have that u converges weakly to u tilde in L2 H1 because I still have that bound. The estimate on the time translates gives me strong convergence of u in this space. But now because I've dropped the Laplace-Beltrami of w, I don't get weak convergence of w in L2 H1. All I get is weak convergence of w in, say, L2, L2. And now I'm kind of stuck because I need strong convergence of w to pass to the limit in the nonlinear term. Or I need strong convergence of the trace of u. And in this case, we can show that these two results here are sufficient to conclude that actually the trace of u strongly converges in L2 gamma cross 0t. And that's enough to pass to the limit in the nonlinear term and verify this constraint holds in the limit, that v tilde is in beta u tilde. And that basically gives you that the pair u tilde v tilde, with v tilde defined to be minus w tilde, are the unique weak solution to this problem here. I'm not going to go through the details of the uniqueness proof because essentially the same idea works to prove uniqueness for this problem here. It's just a little less technical, so I'll just show you the uniqueness idea for this problem. The last problem we considered, which was valid on long time horizons, was when we sent all of these deltas to 0. Then, as I said previously, we only considered Dirichlet boundary conditions on the outer boundary. When we send all of the deltas to 0, we're going to lose the time derivative of u. So the limiting problem looks like an elliptic equation with dynamic boundary conditions, and we still have this complementarity constraint. And of course, because I've lost the time derivative of u, I lose the initial data for u. U just satisfies an elliptic PDE, and all I have is initial data for v, not for u. So we define a weak solution to this problem in exactly the same way we've been defining weak solutions previously. I need a space which encodes these Dirichlet boundary conditions for u. V now lives in this space. I've lost the Laplace-Beltrami of v, so v isn't an H1 gamma. And I test with sufficiently smooth test functions, integrate by parts, and I end up with this weak formulation here, and the constraint that v is in v to u. Okay. So for this problem, because we've dropped the time derivative of u, we no longer have an estimate on the time translates of u. So we don't a priori have any strong convergence of u, and we don't have any strong convergence of w, it appears. So again, both my sequences appear to only weakly converge, and it doesn't appear one can pass to the limit in the nonlinear term. But we still have an estimate on the time translates of w, because we're not dropping the time derivative of w. And what we show in the paper is that L2 gamma is compactly embedded into the space h minus a half gamma, and that actually implies with this estimate on the time translates that w strongly converges in this space here. Okay? So that's a calculation, and one needs to show it, but it can be done. Once you have that, you can pass to the limit in this nonlinear term, because u, the trace of u, weakly converges in L2 h1 half gamma. W strongly converges in this space here, where h minus a half gamma is the dual space of h1 half gamma, and you can verify that this product here converges to 0 in the limit. Once you have that, you actually conclude that the limiting pair u hat v hat with v hat equal to minus w hat are the unique solution of this problem here. And I'll just sketch the uniqueness proof because it's really easy. It's just a couple of lines. We define two solutions to the problem, u1 v1 and u2 v2. We denote by theta u, u1 minus u2. Theta v is v1 minus v2. Then the pair theta u and theta v satisfy this equation here. We define this new variable theta z to be integral from little t to capital T of theta u. Then one actually sees that theta z is an admissible test function in this weak formulation here, so we can set eta to be theta z. And if you do that and do the calculation, the first term just ends up looking like this. And the second term now is theta v times dt theta z. dt theta z is just minus theta u. So we get minus u1 minus u2. And theta v, because v is in beta u, is just simply beta u1 minus beta u2. But beta is this guy over here. So he's monotone, so this term is still a good term. It's positive by monotonicity at beta. So we have that this guy is equal to 0. Now theta u takes 0 boundary conditions on the outer boundary. So having this L2 estimate on the gradient actually tells me that the L2 H1 norm of theta u is 0. When I plug that back into this equation here, I get that theta v is 0. And that's how one gets uniqueness. So now I wanted to digress a little bit and mention to you some classical free boundary problems, because we'll be able to relate the problems we've just derived to these classical free boundary problems. And the two I wanted to talk about were the one-phase Stefan problem, which is, I think it's probably the most classical moving boundary problem, time-dependent free boundary problem. It's a model for the melting of ice, say, into water, so a temperature-dependent phase transition, and we take one of the phases to be at the melting temperature. So in this case, we set the temperature and the ice phase to be 0, and that's why you get the one-phase problem. In the water region, the evolution of the temperature satisfies this equation here, so we have diffusion of heat. This parameter gamma is called the specific heat. On the boundary between the ice and the water region, we have that the temperature equals 0, and the boundary moves according to this law here. So the normal velocity of the boundary is proportional to minus the normal derivative of the temperature. On the outer boundary, for simplicity, you could have 0 flux boundary conditions or something like that. So as I said, this parameter gamma is called the specific heat, and this parameter kappa is called the latent heat. You can think of it as the energy required to turn 1 unit of ice at the melting temperature into water. a related free boundary problem, which you essentially get when you take the zero specific heat limit of the one-phase Stefan problem, is called the Healy-Shaw problem. And here it's a model for, amongst other things, injection of a viscous fluid into a gap between two close together parallel plates. The motion of the fluid in this case can be described completely by the pressure. In the fluid region, the pressure is harmonic. On the boundary between the fluid region and the air, we have that the pressure is equal to 0. And the free boundary between the fluid and the air region moves according to Darcy's law, which is all that this is saying. On this interior boundary, you could have, for example, a constant injection rate of fluid into the domain, and on the outer boundary, you could have, for example, zero flux boundary conditions. So these guys are called free boundary problems because we can't simply solve the equation for p and theta. We have to solve both for p and theta, but also for this domain, or for this boundary gamma t, because the equation is only defined in the fluid region or the air region that we have to solve. So you have to solve for both the geometry and the dependent variable at the same time, hence the name free boundary problem. However, you can try and write down fixed domain formulations for these problems where the free boundary doesn't appear explicitly. And to do that, one introduces these graphs. So this graph is the graph associated with the Stefan problem. It's sometimes called the enthalpy. And this is the graph associated with the Healy-Shaw problem. It's basically just the characteristic function of the pressure. If you introduce these graphs, you can reformulate our free boundary problems into an equation which looks like this. And of course, because this h, these graphs are multi-valued and non-smooth, we have to interpret this equation in a suitable weak sense. There's tons and tons of literature on these types of formulations of the Stefan problem and the Healy-Shaw problem. For example, there's a very nice paper by Crowley in '79, but there's many other works. So the reason I brought up, and one more thing about these problems is that you can look at a transformation of the dependent variable such that you reformulate these problems as variational inequalities. So I think it was Duvaux who showed this for the Stefan problem, and Elliott and Janowski did it for the Healy-Shaw problem. They basically integrated in time the dependent variable. So temperature in case of the Stefan problem, pressure in the case of the Healy-Shaw problem. And you can show that the transformed variables, which are the integrals in time, satisfy variational inequalities. So in the case of the Healy-Shaw problem, you get a variational inequality which looks like this. Basically says that the integral in time of the pressure satisfies the obstacle problem. Okay, that's all this elliptic variational inequality is saying. And the nice thing about this problem is that previously we had a free boundary problem, which we had to solve forward in time. But if we look at this problem here, I can obtain z independently of the values of z at any other times. Time only enters this problem here as a parameter. So if I want to solve the free boundary problem at any given time, I do not need to know the values at any other times. And if you remember my motivating pictures, this should ring a bell. This might tell you where we're going. If you take the one-phase Stefan problem and you look at the integral in time of the temperature, then you get out a parabolic variational inequality, which looks like this. So how can we relate our problems to these classical free boundary problems? At least from what I've shown you so far, that's not obvious, because we had these coupled bulk surface systems of equations. But what we can do is introduce these operators, A delta and A omega, which are basically parabolic and elliptic Dirichlet-Neumann maps. I won't go into all the details of defining them, but I'm happy to talk about them with anyone who's interested. Once you introduce these operators, you can write all of the problems I just showed you as abstract parabolic equations on the surface gamma, so on the surface of the cell. The first one is an equation posed in L2H-1, which is the dual space of H1 gamma in my notation. And the reason it's posed in that space is because we still have the Laplace-Beltrami of V sitting there. The second one is an equation posed in L2H minus a half gamma, and it looks like this, where A delta omega is the Dirichlet-Neumann map of the parabolic extension of U off of gamma. These guys here are just source terms, and they take care of the boundary data and initial data for the bulk equation. And the last one is a similar equation, but I have A0 instead of A delta omega. A0 is just the Dirichlet-Neumann map of the harmonic extension of U of gamma. If you recall the discussion we had on the one-phase Stefan and Healy-Shaw problems, we can think of these two problems here as basically one-phase Stefan or Healy-Shaw problems posed on the surface gamma, where the graph associated with these problems is that graph, B to U. And for the one-phase Stefan and Healy-Shaw problems, we'd see the Laplacian sitting there, but for our problems, we have these strange operators based on the Dirichlet-Neumann map. Furthermore, one can think of this operator A0, which is just the elliptic Dirichlet-Neumann map, as the square root of minus the Laplace-Beltrami on gamma. If one does that, you can see problem 3 as basically the Healy-Shaw problem on gamma, but with the Laplace-Beltrami replaced by this operator here. Okay, so that interpretation is interesting, and indeed we can apply the same techniques that people apply to resolution of the Healy-Shaw and Stefan problems. So we can look at what happens if you integrate in time the dependent variable, and if you do that, you can reformulate these problems as variational inequalities. So if I just look at problem 3, and I look at what the equation, the integral in time, the dependent variable satisfies, it satisfies, at least formally, an equation that looks like this. So the pairs z and v satisfy this system here. All I've done is integrate in time the limiting problem we got for u. The only thing that one has to check is this complementarity, so that v hat is in beta z hat, but that essentially follows from a one-line calculation. It's not difficult to show this. And now one could show that this elliptic equation for z can be rewritten as a variational inequality. And to show that, we introduce this space of functions with 0 boundary values on the outer boundary. We test with an eta that's in the space. We integrate by parts. That gives us this here. Then we define the set of h1 functions that are positive and take the value, this boundary value on the outer boundary. If you recall, this was the boundary value that z had, so z is in the space. So then if we take eta minus z for any eta in this space as well, we have that it's in h1 e0. So it's an admissible test function here, and we can write down this equation here. Finally, I had that the normal derivative of z was simply v0 minus v hat. So that gives me this equality here. And now my complementarity, that v was in beta z, basically all that says is that z is positive, v is negative, and zv is equal to 0. That yields that this that I've written down here is equivalent to an elliptic variational inequality, which is this guy here. You can think of this elliptic variational inequality as a boundary obstacle problem. And the nice thing about this variational inequality, just like we saw for the Healy-Shaw problem, time only enters this as a parameter. So if I want to solve for z, I can do it independent of the values at any other time. And of course, once I have z, I can get v, because v is simply the normal minus the normal derivative of z plus v0. And I can also get u, because u was the time derivative of z. So I could simply solve this problem at any given time and post-process the solution to get back my u, which is the bulk ligand concentration, and v, which is minus the surface receptor density. If we recall that operator A0, which is the Dirichlet-Neumann map of the harmonic extension, in which we identified with the square root of minus the Laplace-Beltrami, then this elliptic variational inequality here can be rewritten as a variational inequality on gamma with this operator, A0. And if we do that, we see that actually problem 3 is just a Healy-Shaw problem on the surface gamma, but with the half Laplacian replacing the usual Laplacian. So that's another way to interpret this free boundary problem we derived. So I want to show you some numerics of all these different problems. We use a very nice numerical method for the approximation, which is based on coupled bulk surface finite elements. There's a nice analysis of the method by Elliott and Rana, who looked at coupled linear elliptic systems. The basic idea is really simple. You take your domain omega and you triangulate it with, say, this green triangulation, and you do standard bulk finite elements for your bulk equations in omega. But then you note that the boundary faces of your bulk triangulation of omega are actually a surface triangulation of the surface gamma. And on the surface triangulation, we do something called surface finite elements. Right? But essentially, the idea is analogous to bulk finite elements. This geometry is not that interesting, so one could look at realistic, more cell-like geometries. So maybe I have an arrow-shaped cell which lives in a square domain. All the interesting stuff in this problem happens close to the surface of the cell, so we use a graded mesh with small elements near the cell surface and large elements away from the cell surface. And as I showed you previously, this can all be done in 3D. Maybe your domain is spherical with this cell-shaped hole inside it, and you can mesh such a domain, and you can also use a graded mesh with smaller elements near the surface of the cell and larger elements near the outer boundary. If we simulate such a problem here, I'm showing you simulations of the original equation, so where I haven't sent any of the parameters to 0 before the limiting problems, but I'm going to be interested in comparing it with one of the asymptotic limits. I'm going to take delta k, delta omega, and delta gamma all to be small. I'm going to take them all to be 10 to the minus 2. For the bulk ligand field, I have Dirichlet conditions on the outer boundary, and initial data all just equal to 1. For the surface receptor density, I have initial data with compact support. So basically where you see light blue, W0 is 0, and where you see dark blue or orange, W0 is strictly positive. And if you run such a simulation, what you see, hopefully, is that you lose ligands near the cell surface where you have receptors, so the concentration quickly goes to 0, but eventually the ligands react with all the receptors and you have no receptors left on the surface, and you just have the ligand concentration in the bulk going to its Dirichlet value. Okay? So to compare with the limiting problems, I'd like to take epsilon very small, but that's hard to do in 3D. Roughly speaking, the smaller you take epsilon to be, the finer your numerical resolution has to be. You have to take smaller time steps and a much smaller mesh size. In 2D, however, I can take smaller values of epsilon. So I'm showing you the same type of simulation in 2D, now with this arrow-shaped cell, which lives in a square domain. And on the right of each of the plots, I'm going to show you the trace of the bulk ligand concentration. That's this black line. So it's the values that the bulk concentration takes on the surface gamma. And the red curves are going to be the surface receptor density plotted along the curve. And as we read from left to right and from top to bottom, we're getting smaller and smaller values of epsilon. So if we simulate this problem, what you see is that as epsilon gets smaller, we really get this separation into a region on gamma where W has support and U is 0, and a region on gamma where U has support and W is 0. You get this, exactly what we said would happen in the limit. This complementarity condition appears. And by the time you've got to 10 to the minus 3, you're almost there. You're almost at the free boundary problem. The supports are almost completely disjoint. Okay? And so to compare this with the solutions to the limiting free boundary problem, we solved the elliptic variational inequality I derived for you, but we want to recover U and W from it. U is simply the time derivative of Z, so we just have to solve this elliptic variational inequality at 2 close together times and differentiate in time numerically. And once we have one value of Z, we can obtain W directly from this formula here. So all I'm solving to generate these pictures here is one elliptic variational inequality posed in omega. I don't have to solve this parabolic equation over multiple time steps. And at least qualitatively, the pictures look similar. But we've also shown rigorously that as you take epsilon to 0, these pictures should start looking much closer together. And indeed, you can see that if you look at the 2D simulations. So as epsilon gets smaller and smaller, we're approaching the simulations of just solving the elliptic variational inequality. There are still quantitative differences, but qualitatively we're getting closer and closer to this bottom guy. And you can see that as well if you look at the solution traces on the boundary. Finally, I kind of told you that this elliptic variational inequality we got can be thought of as a Healy-Shor problem on the surface gamma with the half Laplacian. And here all we're visualizing is the corresponding free boundary. If you interpret our problem 3 as the Healy-Shor problem on gamma, then this would be the position of the free boundary in the Healy-Shor problem. And to define it, we've just taken some small level curve of Z. So we've taken Z equals 10 to the minus 4, I think. What you see is initially you have that I think U is positive in this region and 0 everywhere outside the black curves. And then eventually U covers the whole of the domain and W goes to 0 almost everywhere. So that was pretty much everything I wanted to say. In summary, what have we done? We've demonstrated well-posedness for a very simple model for receptor-ligand dynamics that couples a bulk PDE to a surface PDE with nonlinear coupling. Now this model was very simple, but I think models like this are the building blocks of much more complicated models designed to model biological phenomena. So I think this work was still worthwhile in putting such models on a mathematically rigorous founding. I've proved to you that in a mathematically rigorous sense, the solution to the original model converges to the solution of certain limiting bulk surface free boundary problems in biologically relevant asymptotic limits. We've tried to demonstrate that the limiting problems can be thought of as analogues of classical free boundary problems, but they're now posed on the surface of the cell. And I showed you some numerical results simulating the original problem. And through this analogy with classical free boundary problems, we showed that we could simulate one of the reduced problems in a way that was particularly amenable to computational simulation, and so we got massive computational speed up. In terms of where we want to go, well, I think our original model is too simple. I mean, as we've heard in some of the talks previously, receptor-ligand interactions are much more complicated than this two-component system I eventually considered. But at least in principle, I don't think including more biological details is massively complicated. So one could put in things like receptor degradation, receptor internalization. In practice, you might have multiple species involved in the binding, and you could have more complex binding models. For example, ligands could have to become surface resident before they bind with receptors and so on. All of this, in principle, could go straight in to such an exercise, and you could try and derive limiting problems from a more complicated model for receptor-ligand dynamics. I don't see a big issue with that. Technically more difficult, but also interesting, is to consider the case relevant to applications. So this workshop's about cell motility, and typically for all the applications we're interested in, these cells are moving. So if you're thinking of chemotaxis or substrate adhesion, then you're necessarily considering moving cells. If you wanted to do the same thing with moving surfaces, it becomes much more technical, but that's eventually something we want to consider. Okay, and with that, I'll stop and be early for coffee. Thank you.
Okay, we have certainly time for a couple of questions before coffee.
Yeah, as a physicist, I'm trying to map what you told me to what I learned at some point. In the very first step, you basically set the concentration of the ligands to 0.
No.
Was it?
The complexes.
Complex.
We don't set the concentration to 0. So you can infer the complex concentration isn't 0, but what we said, if I can get back, is that the off rate is 0.
Yes.
Yeah.
And this means you are basically violating detailed balance, so thermodynamics. Can I think of this solution, what you presented as, let's say, the first term in a series expansion to the correct solution if I would take a very small off rate into account, or do you think there would be only a minor change, or would it change the...
I think if you had a very small off rate, there would only be a minor change. But in principle, you don't have to set the off rate to 0. So this is not necessary to do this type of analysis. And that was what I was trying to hint at the end. You could keep the off rate. The analysis would become a little bit more technical, but it could still be done. So this was just for simplicity. At a first attempt, we set the off rate to 0. But it's not necessary, I shouldn't think. I mean, the off rate's a linear term as well. So in terms of the PD analysis, it shouldn't cause huge complications.
Any other questions?
In the spirit of what Alan was showing us earlier, could you carry out some matched asymptotics to understand those solution structures you showed at the end?
I imagine one could, but I haven't thought about that at all. So I can't give you an answer to that question. I'm sure one could, but it's not something we've explored at all. It would be interesting. I imagine for the Stefan and Healy-Shaw problem, people have done things like that, so one quite possibly could.
So thinking of the analogy with crystal growth models, so the Stefan problem has a hierarchy of models too, including effects like undercooling.
Yeah.
So do you anticipate phenomena like that here?
So not in this case. I don't know if you had a more complicated model for receptor-ligand dynamics, whether you could get to. So that would basically change the graph of the Stefan problem into something that wasn't necessarily monotone, I guess. Yes, that could be possible, but I think you would have to start with a more complicated model for receptor-ligand dynamics, and maybe you would get something like that.
Any other questions? Okay, if not, we'll stop there, so we'll have a slightly extended coffee break. First of all, thanks again.